You ever stop and think about what's really going on inside the machines all around us? I mean, it's not just a bunch of gears and motors, right? No, there's this invisible, almost elegant choreography of motion happening. So let's pull back the curtain and dive into this hidden world. So to get started, let me ask you something. What's the hidden link between these? At first glance, a steam train and, say, an industrial metal shaper, they seem totally unrelated, don't they? But believe it or not, they and a simple little diagram we're about to see, they all share this deep mechanical secret. Okay, first up, you've got the raw power, that rhythmic chug-chug-chug of a locomotive's wheels. And then, on the other hand, you have this, the super precise, repetitive dance of a shaping machine, just carving away at metal with insane accuracy. And finally, there's this, just a simple, kind of abstract sketch of connected rods. So what in the world could possibly tie all of these together? Well, the answer is the beautiful science of motion itself. All right, so to really get it, we've got to look past the surface. We need to see the skeletons of these machines. And that brings us to a really important idea. What's the difference between a machine and a mechanism? You see, a machine, that's the whole shebang. It does useful work, right? Like a lathe or a car engine. But a mechanism, now that's the clever bit inside. It's the specific arrangement of parts that makes a certain kind of motion happen. It's literally the bones that let the machine move. Yeah, this quote just nails it. A mechanism is the skeleton outline of the machine to produce motion between various links. It's the pure idea of the motion. Here's a good way to think about it. Every machine has mechanisms inside it, but a mechanism on its own isn't necessarily a full machine. Okay, let's tackle one of the first big puzzles engineers ever had to solve. How do you take the simple, powerful spin of a circle and turn it into a useful straight line? I mean, a spinning motor or a wheel is awesome, but for so many jobs, think about pistons in an engine, or even a simple saw, you need that spin to become a straight back and forth push. So how do you even do that? Well, let's go back to our locomotive for a second. That tie rod connecting the wheels, that is the perfect example. Just look at it. As the wheels spin around, the rod is forced to channel all that circular energy into a powerful, straight-ahead push along the track. It's an absolutely masterful way to convert that motion. And this fundamental trick, it actually has a name. It's called the slider crank mechanism. And I'm telling you, it is the heart of so many machines. From your car's engine to a simple power saw, it's just this elegant solution to one of the most common problems in all of engineering. All right, pretty cool, right? We've turned a circle into a line. But now, let's get even more clever. What if you wanted that back and forth motion to have two different speeds? Yeah, think about that shaping machine again. You need a slow, really powerful stroke to cut the metal, right? But then you want it to snap back to the start as fast as possible so you're not wasting time. So how on earth do you get a slow push and a fast pull from one single constant spin? Well, check this out. The answer is this absolutely brilliant device, the Whitworth Quick Return Mechanism. If you look closely at how it's put together, the magic is all in the geometry. The way the links are connected, that's what creates two different speeds from a single input. It is just pure mechanical elegance. So here's the trick. As that main crank spins at one constant speed, it pushes the cutting tool forward across that really big angle alpha. That's your slow, powerful working stroke. But on the return trip, look, it only has to cover that tiny little angle beta. So naturally, the trip back is way faster. You've got the same input speed, but you get two different output speeds. It's just brilliant. Okay, if you thought that was cool, let's move on to a puzzle that's even more mind-bending. Seriously, this next one feels like actual magic. So picture this. You've got a bunch of rods and they can only pivot at their joints. That means every single part can only move in a circle or an arc. Now my question is, could you arrange them in just the right way to make one single point move in a perfectly straight line? It sounds totally impossible, doesn't it? But guess what? It's not. This right here is Robert's mechanism. And just by picking the perfect lengths and pivot points for these links, that little point P in the middle traces a nearly perfect straight line for a little while. You're literally creating a straight line out of a bunch of circles. How cool is that? Yeah, these things are called straight line mechanisms. And they weren't just a cool party trick, they were absolutely crucial for early machines like steam engines. They made sure the pistons moved perfectly straight without wobbling all over the place. It's proof that with the right geometry, you can force circles to become lines. So you see, all these little tricks we've been looking at, turning circles into lines, getting two speeds from one, drawing straight lines from arcs, they aren't just neat little curiosities. They are the absolute fundamental building blocks for pretty much everything that moves. Remember that simple four-bar linkage from the very beginning? You can think of that as like the simplest sentence in the entire language of machines. And by combining these basic skeletons in all sorts of different ways, engineers can create a practically infinite library of complex movements. And get this, it's not just guesswork. Engineers use really sophisticated tools like these acceleration polygon diagrams you see here to analyze every little piece of the motion. This lets them map out all the forces, all the speeds inside that skeleton, making sure they can design machines that are super efficient, super reliable, and just perfect for the job. So from now on, the next time you see something as simple as a windshield wiper or a pair of pliers or a giant construction crane, I want you to look a little closer. Because you're not just seeing a machine anymore. You're seeing a carefully designed dance of circles and lines. Now that you know the secret, what mechanisms can you spot all around you?